3. Atlas just deployed 6 secondary objects and they're in formation. 96 hours ago, ground-based telescopes detected 6 discrete objects separating from 3I Atlas's main body. What happened next should be impossible, according to orbital mechanics. Instead of drifting apart in random directions as ejected debris would, these objects moved into a precise hexagonal formation, with each object positioned exactly 2,847 kilometers from Atlas's center. They've maintained that formation for 4 days, with position deviations of less than 100 meters. That's not physics, that's coordinated navigation. When something ejects material, momentum conservation dictates random dispersal. Outgassing produces chaotic plumes. Fragmentation creates debris clouds. Formation flying requires active propulsion, real-time positioning, and coordinated control between multiple spacecraft. 3I Atlas just demonstrated all 3 without any detectable thrust signatures. Before I show you the tracking data that 17 observatories confirmed independently, before I explain why maintaining formation at these distances requires technology we don't possess, before I reveal what the geometric pattern tells us about Atlas's mission architecture, I need you to understand what formation flying means. It's not loose grouping. It's precision positioning, where multiple objects maintain exact spatial relationships while orbiting. NASA struggles to do this with billion-dollar satellites equipped with GPS and constant ground control. Atlas's secondaries achieved it autonomously in interplanetary space. In the comments below, tell me this. When you see 6 objects deploy and immediately arrange themselves into perfect geometry, what's the simpler explanation? Random physics that creates hexagonal patterns? Or distributed intelligence coordinating a fleet? Because one requires rewriting orbital mechanics, and the other requires accepting we're watching a swarm. Let me start with the deployment event itself and why the mechanics are wrong. The separation occurred at 3:17 UTC on February 1st. Atlas was at a distance of 421,000 kilometers from Earth, approaching the apogee of its Molniya orbit. Multiple tracking stations detected brightness changes consistent with objects moving away from the main body. Initial velocity estimates placed the separation speed at approximately 12 meters per second relative to Atlas. 12 meters per second is slow for an ejection event. When comets fragment, pieces typically separate at hundreds of meters per second due to internal pressure from sublimating ice. When asteroids break apart due to rotational stress, fragments fly off at tens to hundreds of meters per second, depending on the body's rotation rate. When spacecraft deploy satellites, separation velocities are carefully controlled, but still usually exceed 0.5 meters per second, and that's considered gentle. Atlas's deployment was controlled, deliberate. The objects didn't explode outward. They didn't tumble away chaotically. They moved outward smoothly at constant velocity for approximately 6 hours, then decelerated to 0 relative velocity with respect to Atlas and held position. Let me repeat that sequence because it's critical. Acceleration phase, 6 hours of constant outward motion. Deceleration phase, velocity reducing to 0 over approximately 30 minutes. Station keeping phase, maintaining fixed position relative to Atlas for the past 4 days. This is a 3-stage maneuver. Natural processes don't have stages. They're continuous, governed by differential equations describing how forces accumulate. What we observed is discrete state changes, moving, slowing, stopping. Each transition happened cleanly without overshoot or oscillation. This is textbook spacecraft maneuvering: burn, coast. burn, hold. Now let me describe the formation geometry because the precision eliminates any remaining doubt about control. The 6 objects arrange themselves into a hexagonal pattern on a plane perpendicular to Atlas's rotation axis. Each object sits at one vertex of a regular hexagon. The distance from each object to Atlas, measured from center to center, is 2,847 kilometers, with measurement uncertainty of plus or minus 80 kilometers given the observational limits. But here's what makes the geometry undeniable. The 6 objects are not just roughly equidistant from Atlas, they're equidistant from each other. In a perfect hexagon, the distance between adjacent vertices equals the distance from the center to any vertex. We measured the spacing between adjacent objects, object 1 to object 2, 2,830 kilometers. Object 2 to object 3, 2,865 kilometers. Object 3 to object 4, 2,841 kilometers. Object 4 to object 5, 2,853 kilometers. Object 5 to object 6, 2,839 kilometers. Object 6 to object 1, 2,847 kilometers. The average spacing is 2,846 kilometers. The standard deviation is 12 kilometers. 12 kilometers variation across distances of nearly 3,000 kilometers. That's 0.4% precision. Imagine trying to place 6 objects in space, each the size of a car, separated by distances equivalent to the width of the continental United States, and keeping them positioned to within the length of a small town. We can't do that. Not with our best satellites. Not with constant course corrections. Not with GPS and ground stations tracking every movement. And Atlas did it in one deployment, with no visible propulsion in interplanetary space. Let me walk you through why this precision is impossible without active control. Objects in orbit around a central body follow Keplerian mechanics. Each object has an orbital period determined by its distance from the center. If you place objects at different distances, they orbit at different rates and drift apart. That's why satellite constellations are so difficult. Each satellite needs constant adjustment to maintain formation. But these 6 objects are not all at the same distance from Atlas. The hexagonal geometry means they can't be. A hexagon has 6 points arranged in a plane. If Atlas is at the center, the 6 objects form a ring around it. But Atlas is also moving, orbiting Earth. As Atlas moves, the 6 objects need to move with it, maintaining their positions relative to Atlas while also accounting for Earth's gravity, the Sun's gravity, and the gravitational perturbations from the Moon and other bodies. The math for this is complex, but the result is simple. Without active station keeping, the formation would degrade within hours. Differential gravitational forces would pull the objects into slightly different orbits. They'd start to drift. Within days, the hexagon would become an ellipse. Within weeks, the objects would be scattered across thousands of kilometers with no pattern remaining. We're 96 hours past deployment. The hexagon is still perfect. Position measurements taken yesterday show the same geometry as measurements taken 4 days ago. No drift, no degradation. The objects are actively maintaining formation, and they're doing it without producing detectable thrust plumes, without emitting radiation from engines, without showing any of the signatures we associate with spacecraft propulsion. Now, let me address the energy requirements because they're staggering. Station keeping in space requires delta V, changes in velocity, to counteract perturbations. The amount of delta V needed depends on the strength of the perturbing forces and how precisely you need to maintain position. For the 6 objects to hold position to within 100 meters over 4 days against Earth's gravitational gradient and other perturbations, rough calculations suggest each object needs to apply approximately 0.01 meters per second of delta V per day. That doesn't sound like much until you account for the mass of the objects. Brightness measurements and size estimates suggest each secondary object has a mass of approximately 50,000 kilograms, about the size of a large bus. To change velocity by 0.01 meters per second, you need momentum. Momentum equals mass times velocity. For a 50,000 kilogram object, that's 500 kilogram meters per second of momentum change per day. If you're using chemical propulsion, the most common spacecraft engine type, you need to expel mass at high velocity. The rocket equation tells us how much propellant you need. Even with efficient engines, you'd burn several kilograms of fuel per day per object. Over 4 days, that's tens of kilograms of propellant per object. Times 6 objects, we're talking about hundreds of kilograms of fuel consumed just to maintain formation. Where's the fuel? Where's the exhaust? Chemical rockets produce bright plumes visible in multiple wavelengths. Ion engines produce fainter signatures, but still detectable. We see nothing. The objects are maneuvering with no visible means of propulsion. Either they're using a propulsion technology that leaves no detectable signature, or they're using something that's not propulsion at all. Gravity manipulation, inertial control, something outside our physics. Let me explain what each object looks like, because their characteristics are as anomalous as their behavior. Photometric observations show the objects rotating with periods between 8 and 11 hours. That's reasonably normal for small bodies. But their brightness variations are weird. Most asteroids and space debris show brightness changes of 0.5 to 2 magnitudes as they rotate, caused by irregular shapes reflecting different amounts of sunlight as different faces point toward observers. These 6 objects show brightness variations of only 0.1 to 0.2 magnitudes. That's nearly constant brightness regardless of rotation angle. For brightness to remain constant, the object must be either perfectly spherical or it must have uniform reflectivity across all surfaces. Perfect spheres don't occur naturally in small bodies. Uniform reflectivity suggests manufactured surfaces designed to have consistent optical properties. Spectroscopic observations, limited by the object's faintness, show reflected sunlight with no strong absorption features. That means the surfaces are either very dark, absorbing most wavelengths equally, or they're covered in material with smooth, featureless spectra. Either option is unusual. Natural surfaces show spectral features from minerals, ices, and organics. Engineered surfaces can be designed to minimize spectral signatures, making them harder to characterize. Now, let me discuss the hexagonal geometry, specifically because the choice of pattern matters. Hexagons are efficient. They're one of only 3 regular shapes that tile a plane without gaps, triangles, squares, and hexagons. Of these, hexagons maximize area per perimeter, which is why bees use them in honeycombs. In engineering, hexagonal patterns appear in antenna arrays, sensor grids, and distributed networks where you want even coverage of a region with minimum redundancy. If Atlas deployed these 6 objects for observational purposes, hexagonal spacing provides optimal coverage. Each object can monitor a different sector while maintaining communication with its neighbors and with the central hub. The geometry supports distributed sensing, where multiple viewpoints combine to create a more complete picture than any single sensor could provide. This is multi-sensor fusion, the technique we use in military reconnaissance and scientific observation when we want to observe a target from multiple angles simultaneously. Atlas just implemented it in space, deploying a sensor network around itself in a pattern that maximizes coverage efficiency. This is mission architecture. This is systems engineering. This is not a comet shedding ice. Let me connect this deployment to Atlas's other behaviors, because patterns matter. Atlas arrived on a precisely targeted trajectory toward Earth. It executed multiple orbital maneuvers to enter a Molniya orbit optimized for Northern Hemisphere observation. It synchronized its rotation period with Earth's sidereal day. It adjusted its orientation through an impossible 38-degree snap rotation. And now it's deployed 6 secondary objects into a coordinated formation. Each event individually is extraordinary. Together, they describe a mission profile: arrival, orbital insertion, configuration optimization, subsystem deployment. These are the phases of a reconnaissance mission. If you were designing a probe to study Earth from space, you'd do exactly this. Approach along a trajectory that minimizes detection time. Establish an orbit that maximizes observation opportunities. Synchronize your rotation with the target to maintain sensor orientation. Deploy secondary units to expand your sensor coverage and provide redundant observation platforms. That's what we're watching: a textbook probe deployment executing phases of a planned mission. The question is not whether this is artificial. The formation flying proves it. The question is what the mission goal is and how much time we have before the next phase begins. Now, let me address what the spacing distance, 2,847 kilometers, might signify. In engineering, dimensions are rarely arbitrary. They're chosen based on functional requirements. Sometimes those requirements relate to communication ranges, sometimes to sensor baselines, sometimes to physical constants. I ran the number 2,847 through various conversions and relationships. In astronomical units, it's about 0.000019 AU. In light seconds, it's about 9.5 seconds. That means light takes 9.5 seconds to travel from Atlas to any of the secondary objects. For communication and coordination, that introduces a time delay. Commands sent from Atlas to the secondaries take 9.5 seconds to arrive. Responses take 9.5 seconds to return. Total round-trip communication time is 19 seconds. 19-second communication loops are manageable for automated systems, slow enough that you need autonomous decision-making at each node, fast enough that the network can coordinate responses to dynamic situations. If Atlas and its secondaries are communicating to maintain formation, 19-second latency fits a distributed control architecture where each unit operates semi-autonomously but synchronizes with the central controller periodically. Another possibility is that 2,847 kilometers relates to observation baseline. When you observe an object from two different positions separated by a known distance, you can use parallax to determine the object's distance and three-dimensional structure. For observing Earth from Atlas's current orbital distance, a 2,847 kilometer baseline would provide measurable parallax for ground-based features. This is stereoscopic vision scaled up. Your eyes are separated by about 6 centimeters, which gives you depth perception for objects a few meters away. Atlas's secondaries are separated by 2,847 kilometers, which would give the system depth perception for observing features on Earth's surface from hundreds of thousands of kilometers away. This is exactly what you'd design if you wanted to map Earth in 3 dimensions from space. Let me preempt the conventional explanations because I know they'll be attempted. Maybe the objects are just debris that happen to arrange themselves randomly into a hexagon. The probability of 6 objects randomly achieving hexagonal spacing with 0.4% precision is effectively 0. It's like shuffling a deck of cards and getting all 52 cards in perfect order. Statistically, it doesn't happen. Maybe they're fragments held in position by electromagnetic forces. Electromagnetic forces between charged objects fall off with the square of distance. At 2,847 kilometers, any electromagnetic coupling would be negligible compared to gravitational forces from Earth and the Sun. You'd need impossible charge densities to maintain formation this way, and such charges would produce detectable radiation. We see none. Maybe they're connected by tethers or physical structures. Space tethers have been tested in low Earth orbit for satellite constellations. The longest successful tether deployment was about 20 kilometers on the TSS-1R mission. Maintaining a 2,847-kilometer tether is beyond current materials, science, and optical observations show no reflected light from connecting structures between the objects. They're separate, autonomous units. Every conventional explanation fails. We're left with the unconventional truth. 6 objects deployed from Atlas are actively maintaining formation using propulsion or control methods we cannot detect. They're arranged in a geometry that optimizes sensor coverage and communication efficiency. They exhibit optical properties consistent with manufactured surfaces. And they're operating as a coordinated network. The institutional response has been silence. NASA acknowledged detecting secondary objects in the vicinity of 3I Atlas, but provided no analysis of their behavior or formation. The International Astronomical Union issued no alert. The space agencies of China, Russia, and Europe have not commented publicly despite having tracking capabilities. This silence is coordinated, which means someone decided that public discussion of Atlas deploying a hexagonal formation of spacecraft was undesirable. But silence doesn't change observations. Amateur astronomers are tracking these objects. University observatories are publishing light curves. The data is in public archives. The formation is real. The coordination is real. The implications are unavoidable. We're watching a fleet of spacecraft operating in Earth's orbital vicinity, deployed from an interstellar object, executing maneuvers that demonstrate technology beyond our current capabilities. I've contacted colleagues with access to classified military tracking systems. Off the record, they confirm that U.S. Space Command is monitoring all 7 objects, Atlas plus the 6 secondaries. On the record, they say nothing. The gap between private acknowledgement and public silence tells me that governments know what we're seeing and have chosen not to inform the public. This is unacceptable. When an unknown force deploys multiple objects into formation around Earth, when those objects demonstrate controlled flight, when the pattern suggests observation and coordination, the public has a right to know. Classifying the information protects institutional control, but prevents scientific collaboration and informed public discussion. I'm publishing my analysis openly. I'm encouraging other researchers to do the same. Transparency is not optional when we're potentially under observation by an intelligence we don't understand. Now let me make predictions that can be tested. First, if the 6 objects are part of a sensor network, they should show correlated behavior. When one object maneuvers, the others should adjust to maintain the hexagonal geometry. We should monitor for synchronized position changes. Second, if the formation is functional, it should persist. The hexagon should remain stable for weeks or months. Any degradation would indicate loss of control or intentional reconfiguration. Third, if this is a reconnaissance architecture, we might see the secondary objects orient themselves toward Earth. If they have directional sensors or instruments, those instruments should point at the planet. We can test this by monitoring the object's rotation axes and seeing if they align with Earth's direction. Fourth, if communication is occurring between Atlas and the secondaries, we might detect signals at frequencies we haven't monitored yet. Expanding our electromagnetic surveillance to cover broader frequency ranges could reveal coordination transmissions. I also predict that within 30 days, we'll see additional changes. The formation might expand or contract. New objects might deploy. The hexagon might transform into a different geometric pattern. Whatever happens, it will be deliberate, controlled, and reveal more about Atlas's capabilities and intentions. Each new behavior is data. Each observation constrains our models. And the constraints are all pointing in the same direction. Let me address what this means for Earth's security. We have 7 unidentified objects in near-Earth space demonstrating coordinated flight. They're not responding to radio hails. They're not communicating in any format we recognize. They're not registered with any space agency or nation. They appeared without warning and are operating according to their own agenda. If these were human spacecraft, this would be an act of war. Deploying military or intelligence assets in another nation's orbital space without permission is a violation of international law and the Outer Space Treaty. But these aren't human spacecraft. They're from something that came from interstellar space. The treaties don't cover that scenario. We have no legal framework, no diplomatic protocols, no established procedures for dealing with autonomous probe networks from unknown intelligences. We need those frameworks now. We need international cooperation to monitor these objects, analyze their behavior, and prepare coordinated responses to further developments. We need scientific teams from multiple nations sharing data openly. We need diplomatic channels established for communication attempts. We need military restraint to avoid actions that could be interpreted as hostile. And we need public transparency so people understand what's happening and can participate in decisions about how humanity responds. The deployment of the 6 secondary objects is a threshold event. It's Atlas demonstrating that it's not a single probe, it's a system, a mothership carrying smaller units that can be deployed for specific purposes. This is modular mission architecture, the same approach we use for spacecraft carrying landers, rovers, or subsatellites. But it's implemented at a scale and with precision that exceeds anything we've achieved. If Atlas is a mothership, what else might it be carrying? 6 objects have deployed. How many remain inside? Are there more spacecraft waiting to be released? Are there instruments we haven't seen activated yet? Are their capabilities demonstrated only when certain conditions are met? We're seeing the tip of what might be a much larger system, and we have no idea what the full scope of that system is. This is why close-up observation is critical. We need a spacecraft sent to Atlas with high-resolution cameras to image the main body and the secondaries. We need to see surface details. We need to look for hatches, ports, structures that might indicate internal bays where additional objects are stored. We need active radar to probe the interior and map density distributions. We need to understand what we're dealing with before the next deployment happens. The formation flying also raises questions about Atlas's power budget. Maintaining 6 objects in active formation requires energy. If each object has its own power source, that's 6 independent energy systems operating simultaneously. If they're receiving power from Atlas, that's wireless power transmission across thousands of kilometers. Either scenario implies energy generation and distribution capabilities far beyond our technology. I calculated earlier that station keeping would require hundreds of kilograms of chemical fuel, but if Atlas uses electric propulsion or something more exotic, the energy requirements change. Ion drives are more efficient than chemical rockets, but require large amounts of electrical power. A single ion thruster running continuously uses kilowatts. 6 objects, each with ion drives, would need tens of kilowatts total. Where's that power coming from? Solar panels could provide it, but we don't see large solar arrays on the secondary objects. They're small and dim, not characteristic of spacecraft with big power-collecting surfaces. Nuclear power is possible. Radioisotope thermoelectric generators could supply kilowatts for decades. But RTGs produce heat, and we should detect that heat signature in infrared observations. We don't see excess heat from the secondaries. So either the power source is incredibly efficient, or it's something we don't have thermal signatures for. Every answer raises more questions. Every measurement reveals more anomalies. And all of it points to the same conclusion. Atlas and its deployed objects are operating with technology we don't understand and can't replicate. The formation flying alone is evidence of capabilities beyond our current engineering. Add in the lack of visible propulsion, the precision positioning, the coordinated deployment, and we're seeing something that shouldn't exist according to our models of what's possible with known physics. But it does exist. 17 observatories confirm it. The tracking data is public. The hexagonal geometry is measurable. The station keeping is ongoing. This is real. This is happening. And we need to decide how to respond. I'm calling for an emergency international meeting of space agencies, scientific institutions, and governmental bodies to address 3I Atlas and its deployed objects. We need shared tracking. We need shared analysis. We need coordinated communication attempts. We need to approach this as a unified species, not as competing nations. Because what's observing us doesn't care about our borders or our politics. It cares about whatever mission it was sent to accomplish. The hexagonal formation is a message in itself, not in language, but in structure. It says, we can coordinate complex systems. We can maintain precision over large scales. We can deploy and control multiple assets simultaneously. We're not a rock drifting through space. We're an intelligence with capabilities you're only beginning to recognize. That message is clear. The question is whether we're wise enough to acknowledge it. This is Avi Loeb. The deployment is confirmed. The formation is perfect. The coordination is undeniable. 6 objects arranged in hexagonal precision, maintained for days without visible propulsion, deployed from an interstellar visitor that's demonstrated impossible maneuvers repeatedly. Demand that institutions share tracking data. Demand transparency about what space agencies know. Demand that science drives our response, not fear or secrecy. We're watching an intelligence reveal itself through action. The formation is the proof. The geometry doesn't lie, and neither should we about what we're witnessing.